This lecture is going to remind us about units, converting units, and some mass stoichiometry. So just a reminder that there are SI units, units that scientists are supposed to use for each measurement type. And this is just set up so that way, regardless of the country in which you're doing your work or department, biologists versus chemists versus physicists, we all use the standard units. So the ones that we see a lot of, temperature, we should be using Kelvin. Typically we measure with degrees Celsius and do a quick conversion to Kelvin. Mass, we're supposed to be using kilograms, although in the lab we typically use grams just because we aren't working on the kilogram scale. But we could easily convert to kilograms if necessary, which is why we use grams. So this is just a reminder, there are more SI units here than we will use, but now you've got a reference. Some more SI units, these are looking a little bit more on the physics side, the types of things you would see. We see joules are something you've worked with, hertz. So this is just, again, a good reference. And then when we're dealing with our SI units, we use the metric system to make sure that we're all being consistent. So in the metric system, we have the metric prefixes. This table gives us maybe more than you've seen before. I highlighted the ones in blue, gray, kinda there. Those are the ones that we use most often. So I wouldn't worry about memorizing this entire table, but I would be familiar with the ones that are highlighted. We'll especially use mega, kilo, centa, milli, micro. We even use nano a decent amount. So just be familiar with those metric prefixes. And then here are some conversion factors between different units. Again, don't necessarily memorize these, but they are a good reference in converting between, I mean, just thinking like pressure. There are so many pressure units. There's millimeters of mercury, atmospheres, bar, pascals, PSI, torr. So just here's some conversion factors for those. So let's do an example of just doing dimensional analysis, converting from one unit, a measurement made in one unit, to a different unit. So in this example, we're measuring, we made the measurement 4.3, and then that's micrograms, metric prefix micro, and we're converting that to grams. So whenever I'm doing any sort of dimensional analysis or unit converting, I approach the problem by asking myself three questions. First, what unit am I trying to get my answer in? And in this case, grams is the unit I'm trying to get my answer in. What unit and what is the value of the information that I'm starting with that I need to convert? So that's this guy, okay? And then I need to have a unit factor, a way to convert between them. So in this one, it's a metric prefix, so this is one that I would never give you. The unit factor, you would have to come up with it on your own. So 1 gram is equal to 1 times 10 to the 6th micrograms. Another version of this conversion factor is 1 microgram is 1 times 10 to the negative 6th grams. Either one works. I like the one with the positive exponents because what the positive exponent is saying is there are 1 times 10 to the 6th, which is a million micrograms in 1 gram. So I like to think of it, how many little things make up the bigger thing. The other one, 1 microgram, is 1 millionth of a gram. Saying the same thing, but just from a different perspective. So again, I don't care which one you use, just, do it correctly. Okay, so I'm trying to solve for grams, so I'm going to write that down over here. That's the unit I'm solving for. And then I'm beginning with 4.3 micrograms. And then I need to use my unit factors. So I use this train track, railroad track, lines thing to keep my unit factors separate from my numerator and my denominator. So when we're doing dimensional analysis, we need to cancel out the unit we're starting with. So in order to cancel it, we need to put it in the denominator. So again, I'm going to use the unit factor with the positive exponents. So I'm going to put 1 times 10 to the 6th micrograms on the bottom and 1 gram on the top. And then you want to get in the habit of canceling out your units because obviously this stuff's going to get more complicated. So my micrograms canceled, grams are what are left, grams are the unit that I'm trying to solve for, which means I'm finished. So I'm going to put an equal sign in here and then plug this into my calculator. So 4.3 times 1 divided by 1 times 10 to the 6th is what I need to put into my calculator. So 4.3 times 10 to the negatives. Sorry, I was getting excited. Negative 6th grams. So thinking about significant figures, the 4.3 micrograms measurement has two significant figures, but the metric prefix unit factor, that has an infinite number of significant figures because that's an exact value. So the 4.3 had 2 sig figs, my unit factor had infinity, so my answer has 2 sig figs. It's the less, so 2 or infinity, which one is smaller? The answer to that is 2. If there were, and when you do this in your calculator, this is an exact number. There are no other digits. But on the next one, I'll show you an example of how I'd like you to keep track of the digits that are not significant. So this one, we're doing a pressure conversion from 18.7 psi, which is pounds per square inch, to atmospheres. So I've given some unit factors up there. I've got pounds or psi to the capital PA, that's pascals, and then I've got the conversion factor from pascals to atmospheres. So these would be ones that I wouldn't expect that you have memorized. So this is going to be a two-step process because I don't directly give you a psi to atmospheres unit factor. So when I'm asking myself the question, my questions about this, what unit do I want to solve with, get my answer in? It's atmospheres. So I'm going to come over here and write that down, that I'm solving for atmospheres. And then what am I starting with? Well, I'm starting with 18.7 psi. That's what I'm trying to convert into atmospheres. Okay. So I'm going to just start my calculation. So in order to cancel things out, I need to cancel out psi, so I need to put psi in the denominator, which means I have to use the first unit factor since it's the only one that has psi in it. So I'm going to put 1 psi on the bottom, 6,894.76 pascals on the top. Okay, so I successfully converted the measurement psi into pascals, which is not what I'm trying to get my answer in. So I know I'm not finished with the problem. So I'm just going to continue on. I don't stop. I like to do all my setup first and only plug things into my calculator at the end. That's a personal preference. If you'd rather do one step, plug it in your calculator, that's fine. You just cannot round until you're all the way done. So now I've got pascals and I am trying to get to atmospheres. So I'm going to use the second conversion factor, the 1001,325 pascals are in 1 atm. So my pascals cancel. The unit I have left is atmospheres, which is what I'm solving for. So I'm going to go and put my equal sign in and plug this into my calculator. 18.7 psi times 6,894.76 divided by 101,325. I ignored the ones because multiplying and dividing by 1 doesn't change anything. So sig fig wise, 18.7 has 3 sig figs. This unit factor, the pascals psi, 1, 2, 3, 4, 5, 6 significant figures, and the atmospheres in pascals also has 6. So I've got 3 sig figs, 6 sig figs, 6 sig figs. So my answer has the least amount, which is 3. So when I do my calculator, 1.27, sorry, I'm drifting, those all 3 need to be significant. But usually, especially in this class, once you do a calculation, you're not finished. You're probably going to need that number later. So you don't want to really round it because you need those extra digits, because we never want to round a value until we're completely done with the calculation. Again, you might think you're done with a calculation and that you're not going to need that number again, but likely you will need it later. I'm just especially thinking labs. So it's a good idea to get in the habit of keeping a couple digits that are beyond the correct number of sig figs. So this has needed 3 sig figs. Well, I am going to write down, the next 3 digits that were on my calculator, but I would write them kind of as subscripts to remind myself what's significant and what's not. So I'm going to try to rewrite this so it's not quite so weird looking. So 1.27, these are significant figures, and then 2, 4, 6 are the next 3 digits, and the unit is in atmospheres. Wow, that is okay. Anyway, hopefully that makes sense though with the carrying the digits forward as subscripts, so you don't get yourself confused on sig figs, but yeah, you're not leaving stuff behind. Okay, so we did the metric prefix conversion and just unit factor conversions. Hopefully this is not a new concept, the idea of a mole. 1 mole is Avogadro's number, which is 6.022 times 10 to the 23rd of something. So if I have 6.022 times the 10 to the 23rd pencils, I have 1 mole of pencils. If I have 6.022 times 10 to the 23rd atoms of hydrogen, I have 1 mole of hydrogen atoms. If I have 6.022 times 10 to the 23rd elephants, I have a mole of elephants. It doesn't really matter. This can be used for anything. It's only really used for chemistry because that is a ginormous number. So we don't have that many pencils or elephants or whatever, but we definitely have that number of atoms. Okay. But when we're in the lab, we don't count out the number of atoms and molecules. So the easiest way to figure out how much we have is by mass. So the molar mass, which I always abbreviate it with a capital M there, is the sum of the average atomic masses, which we get from the periodic table. It's the value with the decimal places. That's the mass in 1 mole. So that is different for every compound that has a different chemical formula because each element has its own average atomic mass. So it's, again, the number of grams in 1 mole. So usually the units are shown grams per mole. Okay. So there's the periodic table. The values that we're looking at to get the average atomic masses are these decimal values at the bottom. And if you look at this periodic table, it's the one that I will give you in class. It has a lot of decimal places. There's a lot of sig figs. Like, look at this aluminum. A lot of sig figs. When you're calculating your average atomic masses, you're adding them together and getting your molar mass, you need to use the entire thing. Don't round this. Oxygen is 15.9994. Don't write 16. That's wrong. Why would you do that? They did this calculation with the correct number of sig figs, so use them. You have to use the entire molar mass. I don't care what your last chemistry teacher had you do. This is how it works in here. You're going to use the entire molar mass. So when we're dealing with chemical reactions, we have another unit factor that we can apply, and that is the mole ratio. So the mole ratio can only be used with a balanced chemical equation or when we're comparing 2 different chemicals. So this balanced net ionic equation, so we cancel out the spectator ions, we've got 1 mole of thorium to 4 moles of fluoride, and to 1 mole of the thorium for fluoride solid. So down below I have 3 different versions of what the mole ratios I could get out of this equation are. You choose whichever 2 substances you're interested in calculating between, and those are the 2 substances you use to get your mole ratio. It doesn't matter if they're both on the same side of the arrow, if they're both on different sides of the arrow. It really doesn't matter. So you just pick the 2 substances you're interested in. So let's do an example with our molar mass and our mole ratio. So I did one where I'm combining all of that. So we're jumping right in first. So this is stoichiometry. Anytime we're using a mole ratio, technically the calculations we're doing are stoichiometry. So in this problem, I've got a balanced chemical equation given, and the question asks us to calculate the mass of calcium carbonate, and I gave the molar mass, that's what that capital M stands for, up there, which means I already added it together for you. You're welcome. So we're trying to figure out the mass of calcium carbonate that was produced if 2.8041 grams of sodium chloride was also created in this reaction, and then there's the molar mass of sodium chloride. So in this reaction, the chemicals that we're interested in, aren't we trying to get information about calcium carbonate? And we were given information about sodium chloride. So when I do my calculation, those are the only 2 chemicals out of this balanced equation that I am interested in. So I'm still going to do my same steps. I figure out what unit I'm solving for. So we're actually supposed to calculate the mass of calcium carbonate. So I'm going to write grams of calcium carbonate is what we're solving for. Okay. And the information we were given is 2, that's beautiful, 0.8041 grams of sodium chloride. So I just need to start doing unit factors to cancel out grams of sodium chloride until I get to grams of calcium carbonate. So the unit factor I can use to cancel out grams of sodium chloride is the molar mass. So according to up there, 58.44246928 grams are in 1 mole of sodium chloride. Again, I'm getting that from the value that says mm after up there in parentheses, where I added up 1 sodium and 1 chlorine. Okay, so I can cancel out grams of sodium chloride at this point. Now I have moles of sodium chloride, and again, I'm trying to get grams of calcium carbonate, so I need to get rid of the sodium chloride information and convert it over to calcium carbonate, which is when we want to use our mole ratio. So from the balanced equation, 2 moles of sodium chloride are equivalent to 1 mole of calcium carbonate. Again, I got these numbers as the coefficients from the balanced equation. There's a 1 there and a 2 there. Cancel out moles. And then my last step, I've got moles of calcium carbonate, but I need grams, so I'm going to use the molar mass, but this time of calcium carbonate. And this number was given in the problem, 100.0869. All right, so then I would plug this whole thing in my calculator. 2.8041 times 100.0869 divided by 58.44246928, and also divided by 2. Okay, so when I'm looking at this problem, my answer for sig figs is going to be 5, because the initial mass was 5 sig figs. This molar mass has more than 5. The 1 to 2, the mole ratio is an exact number, so it's like infinity. And then this molar mass has, what, 7. Okay, so 5 is the fewest number of significant figures I've got. So, but I don't want to round all the way yet, so I'm going to stick with my plan of doing the little subscripts. So I'm going to write down the first 5 significant figures, 2.4011, that's 5 sig figs. So round to the correct number of sig figs, that's my answer. But I am going to go ahead and keep the next 3 and write them as subscripts. I'm going to rewrite the grams since it's all the way over there. Go away. Okay, so my answer, 2.4011 grams of calcium carbonate, but I kept those extra 3 digits just in case I need them later. So this is going to be a reminder of limiting reactant problems. So it may have been a little bit since you've done one of these. We don't do them a ton, but they will come up sometimes. So in a limiting reactant problem, we're just doing stoichiometry. Same type of problem as the last one, only in this case, you're going to be told how much of each reactant, each initial substance you were given, and then we need to figure out which one will be the limiting reactant, which is the one that runs out first. So because when we're mixing the two things together, one of the ingredients, if you want to think of it as an ingredient, is going to run out and then the reaction has to stop. So we can't just eyeball this and figure out which one's going to run out first because of our lovely molar mass and mole ratio things. So there are many ways to approach limiting reactant problems. So I'm going to show you the way I do them. If you do them a slightly different way, that's fine. Just double check we got the same answer and we're good. So when we're doing limiting reactant problems, so in this one we've got a balanced equation, we're told that they mixed 135 grams, I'm just going to write it underneath here, maybe. 135 grams of aluminum was mixed with 105 grams of the iron 3 oxide. You can't just say, oh, well, the iron 3 oxide must be the limiting reactant because 105 is smaller than 135. Grams are not equal, or their molar masses are different, so you can't judge that, okay? So, anyway, just got that information down there. The way that I always solve these, we're trying to figure out the limiting reactant and the mass of aluminum oxide that was produced. So I'm going to do this as a stoichiometry problem where I'm solving for grams of aluminum oxide because that's what the problem asks me to do. And I'm just going to do this calculation twice, once starting with each reactant. So I started with aluminum. So I'm going to start over here, 135 grams of aluminum, and I'm just going to do some stoichiometry to get my answer. So I'm going to use the molar mass of aluminum, which I gave up there, 26.9815386, and 1 mole of aluminum. I'm going to do the mole ratio, so 2 moles of aluminum, based on the coefficient, to 1 mole of aluminum oxide, since that's the chemical I'm trying to get my answer for. And then I'm going to use the molar mass of aluminum oxide to get it in grams. So the aluminum oxide is 101.9612772. Okay, so cancel, 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 cancel. Grams of aluminum oxide. So what I got was 255. I would have 3 sig figs, but I'm going to keep 3 more digits. 0.078 is the mass of aluminum oxide that I calculated I would make based on the amount of aluminum that I have. So if I had 135 grams of aluminum, we'll make 255 grams of aluminum oxide. What we have to decide is how much can I make from the iron 3 oxide. So I'm just going to redo this calculation. Still solving for grams of aluminum oxide, but this time I'm going to start the problem with 105 grams Fe2O3 and just redo the stoichiometry using this new chemical. So the molar mass of Fe2O3 is 159.6882, 1 mole of Fe2O3. Then I'm going to do the mole ratio between the iron 3 oxide and the aluminum oxide. So 1 mole of Fe2O3 to 1 mole Al2O3, and then molar mass. All right, and then things will cancel. Cancel, 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 cancel. Plug this all into my calculator. I would also have 3 significant figures here. So I get 67.0 would be my 3 significant figures, and then 427 are the next 3 digits. So I had enough iron 3 oxide to make 67.0 grams of aluminum oxide, and I had enough aluminum to make 255 grams of aluminum oxide. What this is telling me is the Fe2O3 is going to run out after I make 67 grams. So that's how much I would actually make, because once I've made 67 grams, the Fe2O3 is gone, the reaction stops. So the answer to what is my limiting reactant, it's the iron 3 oxide. And what is the mass of aluminum oxide that would be produced? 67.0 grams. Again, I've got the unrounded version down there for use in the future. And I am fine if you guys give me a final answer that looks like this, where you've got the other digits, as long as I can clearly tell which ones are significant and which ones are not. All right.